Welcome to qnawire.
This is problem number 33 of the Stewart Calculus 8th edition, section 2.8. Part A. If f of x equals x to the fourth plus 2x, find f prime of x. Okay, let's use the derivative definition to find f prime of x. Limit as h approaches 0 of this function, f of x, evaluated at x plus h. So that means x plus h quantity to the fourth power plus 2 times x plus h. And then we're going to subtract the function f of x, x to the fourth, plus 2x. Is all divided by just h. Okay, good. Next step is to expand every term. Here we have a binomial to the fourth power, and then distribute some other numbers as well. So this binomial to the fourth power will be x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth. That's just this binomial to the fourth power. Then we're going to distribute the 2 here to the x and the h, so plus 2x plus 2h. And then we're going to subtract x to the fourth and 2x as well. Okay, and this is all over h. Now let's take a look at the numerator and see what we can cancel out. We have a positive x to the fourth and a negative x to the fourth. So those go away. A positive 2x and a negative 2x. And then an h in the denominator will cancel with an h in each of the terms in the numerator, since each of the terms in the numerator have at least one h. Okay. So what we're left with is the limit as h approaches 0 of 4x cubed plus 6x squared h plus 4x h squared plus h cubed plus 2. Now as h approaches 0, each of these h terms approaches 0, so those go away, and we should be left with 4x cubed plus 2. And this will indeed be our derivative, f prime of x. Now we will verify in part B by checking our answer with part A to make sure that it's reasonable, comparing the graphs of f and f prime. So we're going to plot both f of x, x to the fourth plus 2x, and f prime of x, 4x cubed plus 2, and see if it is if this answer is reasonable. So we have pulled up f of x, which is in blue, and the derivative, which is in green here, with the functions that we were given and which we found. And let's discuss whether this makes sense. The function f of x is something similar to a parabola. So on the left side, it's decreasing, and when it's decreasing, its slope is negative. So it has a very large negative slope, but then it gets less negative as it gets closer to this minimum point. So that's what we see here. The function, the green function, the derivative function, is mostly negative until it reaches, until it keeps approaching y equals 0. So approaches a slope of 0 exactly where the minimum is. So this is consistent. The slope is 0 at the minimum, so that is correct. Afterward, the slope increases. The slope is positive for the remaining part, and this is shown on the slope graph, the derivative graph in green. And what we see here is that the slope increases and then stays the same for a little bit and then increases again. And that's what explains this behavior here. The slope is positive initially and increases and becomes more positive until a point here. Actually, the slope seems a little constant, exactly equal to around 2. So the slope stays constant for a little bit, but then it starts increasing again. And so this derivative that we found algebraically is consistent with our two graphs shown here.